Hello, hello, hello. This is Nicholas on doing his final third video on this lovely Tuesday afternoon. Wanting to share with you something absolutely wonderful that proves just a plethora of other important identities in number theory. And this is the idea of using matrices for the Euclidean algorithm instead. See, traditionally, right, we'll break it down, right, we're trying to find the GCD of two numbers, A and B, and we'll break A into B Q sub 1 plus R sub 1, and then we'll break down B into R sub 1 Q sub 1 plus R sub 2. We'll break down even further R sub 1 into R sub 2 Q sub... Oh, I messed up on my subscripts. Q sub 2 and Q sub 3. Yeah, plus R sub 3. And so on, right? Eventually, we'll get to the point where we have a Rn minus 1 plus Qn minus 1, Rn minus 2, and that's going to be equal to Rn minus 3. And then at that particular point, we're going to get an Rn, the last non-zero remainder, and then that's going to be our greatest common divisor. Now, what I want to do is, and this might seem a little strange at first, but trust me, it'll make sense, is I'm going to let Q sub I, a matrix, be equal to Q sub I little q sub I. So little q sub I being one of these q's right here, one of these quotients, right? 1, 1, 0. I'm going to let Q sub I be that matrix. And basically what I'm going to show is that, first, I'm also going to let Q be the product of all these matrices. In other words, the product of the matrices formed by all of the remainders. Right, up until the point of where we get a plus 0, right? In other words, we get a Rn minus 1 equals Q sub n R sub n plus 0, and Rn minus 1 would be the GCD. So in other words, it's the product of all of these quotients right here. All of these quotients right here. I moved the Q over. So what I'm going to show then is that the matrix formed by the two numbers that we wish to find the GCD of is equal to Q times the matrix of the last divisor and 0. In other words, the GCD, Rn. That should be at Rn minus 1, and that should be at Rn minus 2. Yeah, there we go. I just mixed. So I guess we would write that like that. In other words, in general, I got kind of caught up in the subscripts there, but in other words, the matrix formed by the two numbers we wish to find the greatest common divisor of is the product of all of these matrices formed by the distinct quotients times the matrix basically with the greatest common divisor that we get from the Euclidean algorithm. And so basically it's such a cool proof. So the matrix AB, and it's so simple too, is, okay, if we look at A, right, what is A? A is B Q sub 1 plus R sub 1, and B will stay the same. So, and this is where this special matrix comes from, because if you notice, this matrix right here can actually be written as Q sub 1, 1, 1, 0 multiplied by the matrix B R sub B R sub 1. Yeah. Because notice, if you do this matrix multiplication, for example, Q sub 1b plus R sub 1, q sub 1b plus r sub 1 is the first right here. And then for the second row, we get 1 times b plus 0, so just a b. And so this is where this matrix and why I actually brought this matrix up, that's where it comes from. It comes from the fact that we can separate it up right here. Now, if I then look at, and this is kind of, it gets recursive right here. If I then look at B R sub 1, that matrix, well, B from the Euclidean algorithm is R sub 1 Q sub 2 plus R sub 2, and then R sub 1 will keep the same, which is nothing but Q sub 2, 1, 1, 0, times R sub 1, R sub 2. And you can, again, check that for yourself with matrix multiplication. Eventually, we'll get down to the point where, in essence, see, now this B sub 1, R sub 1, that was right here, I can replace with all of this. So now I'm going to have now 2 of these remainder matrices multiplied by the matrix formed by the, or I'm sorry, 2 of these quotient matrices right here, and then multiplied by another remainder matrix. And then that remainder matrix, you see, would be equal to, if I have R sub 1, R sub 2, that's going to end up being equal to Q sub 3, 1, 1, 0, times R sub 2, R sub 3, right? And we can keep on doing this. Eventually, we're going to get to the point where the matrix AB is equal to, we would have Q sub 1, 1, 1, 0, Q sub 2, 1, 1, 0, so on, right? Up to the point where we'd have Q sub n, right? 1, 1, 0, multiplied by R to the n, or R sub n, the greatest common divisor, and then 0. Because eventually the remainders will go to 0 by the well-ordering principle. And so this tells us that, well, what is this, right? This is the product of all those quotient matrices, which I defined to be Q. And so therefore, AB is equal to Q times R sub n 0. QED, right? I'll do the little. But now we can take this multiple steps further, because if I multiply by Q inverse on both sides, right? And since matrix multiplication is not commutative, I have to be a little careful here, right? I have to multiply by the Q right here, right? I can't just put it right here. It has to be up front, because that's where I did it up here, up front. Notice that, well, Q inverse Q is just I, the identity matrix, multiplied by that is still just this matrix right here. So now we get that Q inverse times AB is equal to R sub n 0. And so let's say Q inverse now, and notice that, okay, originally if Q is the product Q naught times Q1 times Q2 dot 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 up to Qn, and actually we don't need the Q naught here. If it's Q1 times Q2 times Q3 dot 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 up to Qn, right? And Q inverse is the opposite of that, and matrix multiplication is not commutative, so you have to be careful here. Then Q inverse is going to be the product, and it's going to be reversed, right? So Q inverse is going to be the product Q sub n. It's going to start with the last quotient inverse times Qn minus 1 inverse dot 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 up to Q1 inverse, right? But so if we let this, after we do this matrix multiplication, we're going to get another matrix. It's going to be Q inverse, right? If we let that matrix be equal to, say, alpha, beta, gamma, and delta, because I'm fluent in Greek alphabet. No, not really. If we let that be that matrix, then we would say that alpha, beta, gamma, delta times AB is equal to r sub n 0. And this is so powerful because it establishes so many identities right here, right? For example, by matrix multiplication, we see then if two matrices are equal, their corresponding entries are. And so in other words, alpha times A plus beta times B is equal to R sub n, which by the Euclidean algorithm is the greatest common divisor of A and B. And so this identity, the fact that the linear combination of A and B can be always written as the GCD of A and B, as we've seen, is what's known as Bezóuts identity. And it's extremely helpful because it establishes so many other things. For example, from this matrix proof here, we now know that any Diophantine equation, ax plus by equals the GCD of AB, can be solved no matter what. And we just showed the existence of the solution, right? We showed that the solution is the GCD of AB. So therefore, right, all we'd have to do is use the Euclidean algorithm to find what the GCD of A and B is, and then we could solve that Diophantine equation because, well, notice, right, in this matrix multiplication right here, we get exactly that solution. The answers for x and y are x is going to be alpha and y is going to be beta. So this matrix right here, the value for alpha and the value for beta tells you the numbers, the integers x and y, alpha and beta, such that the GCD of those two numbers can be written as a linear combination of those two numbers. And so therefore, any Diophantine equation of this form can be solved, and also any Diophantine equation, any linear Diophantine equation, ax plus by equals, say, L, where L is some constant times the GCD of A comma B. So in other words, we just need, we just need the fact that whatever number is on this side of the Diophantine equation, say the number on this side is 14, but the GCD is 7, all we know that there has to be a solution, and we know that there is a solution when the left side, or when the right side of this Diophantine equation is a multiple of the greatest common divisor of A and B. So in other words, usually how you'd see it written in a textbook is ax plus by equals c. So we know that a solution exists when the GCD, or when C, if we have, oh my gosh, when the greatest common divisor, when C is a scalar multiple, all right, when C is equal to L times the GCD of A and B, or in other words, the GCD of A and B divides C. So we have a solution existent when that's the case. Now, even further, we know that from the second, when I do this row dotted with this column, I get that gamma A plus delta B is equal to 0. And so that tells me that. Now, if I were to multiply by some k right here, some constant k, right, it'd still be equal to 0 for k element of the integers. Then that tells me that, see, this before was a particular solution. This was just one solution, but now we can actually find a whole family of solutions, right? When I was going through this right here, this generates us one particular value of x and one particular value of y, namely alpha and beta. But now if we know that alpha A plus beta B is equal to the GCD of A and B. And we know that, and I'll write it like gamma Ka plus delta Kb is equal to 0, then I can add these two equations together, and I'll get that A times gamma K plus alpha plus B times delta K plus beta is equal to still the GCD of A comma B. And so this tells me all possible solutions, because K can be any integer, to any linear Diophantine equation of the form ax plus by equals c. And it tells me that because it is all from what I get from this matrix right here. So every value in this matrix is extremely significant. And furthermore, we know that this is a family of solutions, because and we know that it's the work trick, I can add 0. And then beta was our particular solution, right, from over here. And then so was alpha. But still, I can add k multiples of gamma and k multiples of delta, and I'm still going to be equal to the GCD of A and B, because k multiples of alpha times A plus k multiples of delta times B was originally 0. And that was a lot for this one particular video, but that matrix just gives a byproduct to so many cool identities. And knowing especially Bezóuts' identity, that the linear combination is always the linear combination of two numbers is always can be written as a scalar multiple of the greatest common divisor of those two numbers, is extremely helpful when you get later on into more number theory. And I think with that,